Good morning, students. Today we will study the topic quantum numbers. Now, what are quantum numbers? These are the set of four such numbers which give us complete address of an electron. Just as we need a country, city, street, and house number to locate a person, we need a set of four unique quantum numbers to describe the energy state and spatial location of an electron within an atom. So, what are the quantum numbers? These are the set of four such numbers which give us complete address, or we can say complete information about the electron in the structure of atom. Now, what are those four quantum numbers which give us complete information about the electron in the structure of atom? These four quantum numbers are number 1, you can see here, that is first one is principal quantum number, which is denoted by small n. Then second one is azimuthal quantum number. Third one is magnetic quantum number. And fourth one is spin quantum number. Now we will study these separately one by one. You can see here first quantum number we will explain here, that is principal quantum number. First remember it is denoted by small n. And this quantum number, this was proposed by Bohr, and this quantum number indicates about the number of shell where the electron is present. It tells us about the number of shell where the electron is present. So it is represented by the integer small n. Its value may be 1, 2, 3, 4, so on. And these shells, because it tells us about the number of shell, these shells are designated as K, L, M, N, etc., in which the electron resides. Now this quantum number, this also indicates the average distance of the electron from nucleus, effectively defining the atomic radius. So this quantum number, this also helps to find the atomic radius. Now after that, as the value of n increases, the electron's energy and distance also increases. Now the maximum capacity of the electrons accommodated in specific shell, that will be 2n square. So maximum electrons that can be accommodated in a specific shell, that will be equal to 2n square. For example, you have first shell, that is K shell. It will have how many electrons it can accommodate? 2 into 1 square. First shell, K shell is the first shell. So the value of n here, 1. So it becomes 2 into 1 square, that becomes 2. It means first shell can accommodate maximum of 2 electrons. Similarly, second shell, that is L shell, that will have 2 into n square. N means here the value of n in L shell, that is 2. 2 square it becomes, and 2 into 2, 4, 4 into 2, 8 electrons. So second shell can accommodate maximum of 8 electrons. So this is the principal quantum number which gives us certain informations about the electron. First of all, it tells us about, that is, in which shell the electron is present. Second thing, it tells us about the average distance of the electron from the nucleus. Third is, it tells us about the electronic energy present in particular shell. So these are the features of the principal quantum number which gives us information about the electron. Now here, this is the first quantum number. Now we will study the second quantum number, that is azimuthal quantum number. This azimuthal quantum number, that is also referred to as orbital angular momentum quantum number. It can be also referred as angular quantum number. It determines the number and types of subshells. What does it indicate? It tells us about the subshells. For example, you have here we can calculate the number of subshells with the help of this quantum number. This quantum number gives us the information, that is the electron in which subshell electron is present. Okay, so this quantum number tells us about the number of subshells. So it determines the number and types of subshells. And for example, in the way we have designated the shells like KLMN, similarly subshells can be designated as SPDF, present within a primary energy level. Now these crucially defines the three-dimensional geometrical shapes of the electron orbital cloud. For any given principal quantum number n, the permitted integer values of L that range from 0 to n minus 1. In last slide, we have seen about the principal quantum number values. That is, if n equal to 1, this indicates K shell. If n equal to 2, it indicates L shell. If n equal to 3, it indicates M shell, and so on. Similarly, in case of azimuthal quantum number L, the value of L that can be calculated by the formula 0 to n minus 1. It means this is azimuthal quantum number. The value of azimuthal quantum number can be calculated from the value of principal quantum number. How it can be helpful to calculate? For example, you have a first shell. In first shell, n is equal to 1, L is equal to, now we will calculate the value of L, that will be 0 to n minus 1. Here n is 1, 1 minus 1, 0. Means L is having only one value, that is 0. Now here the values of L that indicates, that is which subshell is there, or in which subshell the electron is present. So here in first shell, where the value of n equal to 1, only one subshell is there, which will be referred to as S subshell. Similarly, another examples we can take here. If you have fourth shell, for example, we have fourth shell. Here n value of principal quantum number, that is because we know that here we are considering fourth shell. So fourth shell means value of n equal to 4. Now we will calculate the value of L here, which tells us about the number of subshells present in that respective shell. So in fourth shell, how many subshells will be present? That we can calculate from the value of L. Now the value of L will be 0, 1, 2, 3. 0 से लेके n minus 1 तक. It means 0, 1, 2, 3. So here the value of L equal to 0, that shows S subshell. If value equal to 1, value of L equal to 1, it indicates P subshell. If value of L is equal to 2, it can be designated as D subshell, then F subshell. So here, how many subshells we have shown? S, P, D, F. There are 4 subshells in fourth shell. So from the value of fourth shell, or we can say from the value of n, we can find the value of L. And when we find the value of L, we can show that how many subshells are present in that respective shell. So we have recognized here subshells. So second quantum number, it mainly tells us about the number of subshells present in a shell. So first quantum number, that indicates, that is principal quantum number, that indicates about the number of shells. And second quantum number, azimuthal quantum number, it mainly indicates about the number of subshells present in a shell in which the electron present. So now next we will proceed toward our third quantum number. That is magnetic quantum number. This is our third quantum number, that is magnetic quantum number. Now this magnetic quantum number, it is denoted by M. Magnetic quantum number is denoted by N generally. Now it indicates about the spatial orientation of the electron. It indicates about the orientation of the electron. And introduced to explain the Zeeman effect, this number dictates the permitted spatial orientations of orbitals in a subshell when subjected to an external magnetic field. Now for a specified value of L, the magnetic quantum number ranges from this is we can say minus L to 0 to plus L. Clear? So M, it's total distinct values that will be given by 2L plus 1. So here two formulas we can show. That is, either we can calculate, count the total values from minus L to 0 to plus L, or we can calculate 2L plus 1 values, right? So these two values, they indicates about the spatial orientations, and these spatial orientations, they represent about the number of orbitals present in a subshell. So magnetic quantum number, like you have studied previous quantum number, that is azimuthal quantum number, that tells us about the number of subshells. Now this third quantum number, this tells us about the number of orbitals this magnetic quantum number, this tells us about the total number of orbitals present in a subshell, and its value I have told you, either we can calculate 2L plus 1 value, or we can count the values from minus L to 0 to plus L. For example, now here we can consider some examples. Like for example, we have third shell. Right? In third shell, the value of n is equal to 3, and the value is equal to 0, value of L equal to 0, 1, 2. This indicates S, P, D subshells. You know that value of n, this indicates about the number of shell. The value of L indicates about subshells. Now the third quantum number which we are studying here, that is M, its value indicates about the total number of orbitals present in different subshells. Now here you can say that here S is for S subshell, the value of L is equal to 0. So M, how we can calculate M? Its value we can calculate by this formula, 2L plus 1. You can substitute here for S subshell, how many orbitals in S subshell will be present. You can see here the value of L for S subshell, that is 0. So 2 into 0 plus 1, right? So it becomes 1. It means 1 orbital, the value of M is 1 here in case of S subshell. So it means S subshell have 1 orbital. Clear? Now second subshell, P subshell. In third shell, there are 3 subshells, 3 type of subshells. Now these 3 type of subshells, individually we will calculate the number of orbitals in all these 3. First we have calculated the number of orbitals in S, that is equal to 1 orbital we have calculated. Now for P subshell, we will calculate the value of M. M is equal to, again that formula, 2L plus 1, 2 into what is the value of L for P subshell? This is equal to 1 plus 1. 2 into 1, 2 plus 1, 3. Means 3 orbitals will be present in P subshell. Similarly, for D subshell, we can calculate for d subshell, the value of L is equal to 2. So formula again, M की value आप calculate करोगे 2 into 2 plus 1. This becomes equal to 5. It means d subshell contain how many orbitals? 5 orbitals. So in this way, our this third quantum number, that is magnetic quantum number, it tells us that it tells us the total number of orbitals present in a given subshell. So this is third quantum number. Now next we will proceed toward fourth quantum number. That is spin quantum number. This is fourth quantum number, spin quantum number. It is denoted by S. Now it describes what are its features. It describes the intrinsic spin angular momentum of the electron revolving on its own axis, independent of its orbital motion. An electron can spin in only two specific directions. This we have to remember. This quantum number tells us that an electron can have specific spin in two directions. So electron can spin in only two specific directions, that is clockwise or anti-clockwise, right? Now these two permitted values can be denoted as, ये जो two permitted values हैं, these can be denoted as plus half and minus half. Plus half for spin up and minus half for spin down. Now this quantum number is fundamental to understanding the magnetic properties of bulk substances and rules of electron pairing. So spin quantum number, it indicates us about the main you have to learn here, that is spin quantum number. It is denoted by small s and it indicates about the spin of electron, which can be either clockwise, which can be either clockwise or anti-clockwise. Clockwise or anti-clockwise. And these spin can be represented as plus half and minus half. So for an electron, the values of S, this is equal to plus half and minus half. Clear? This is the fourth quantum number, that is spin quantum number, that tells us